Objectives for today. You will need to be able to describe what kind of information scientists can gather about stars from Earth, so from here on Earth, and how they gather that information. So what tools are they using? You will need to be able to select an appropriate unit of measurement for different ranges of space. So there are different units of measurement we use in outer space, and it depends where in outer space you're measuring, which one you use. So you'll need to be able to pick. And then you will need to be able to tell me the difference between apparent magnitude and absolute magnitude. So those are two vocabulary words you're going to need to know by the end of today. All right? Let's begin with an obvious statement. The night sky is filled with stars. Stars are stationary, like our sun, but from here on Earth, they appear to be moving because even though they are stationary in the sky, the Earth rotates on its axis once every 24 hours, and it revolves around the sun once a year, which means because we are moving in space from Earth, it looks like the stars are moving. That's why different stars are visible not only during different times of night, but also during different seasons of the year, and also depending on which hemisphere of the Earth you're on. Astronomers use groups of stars called constellations, which we learned about yesterday, to break the sky up into zones. We talked about yesterday that there are 88 ancient constellations that were discovered, isn't the right word, but named by ancient scientists. And today's scientists use those 88 constellations to break the sky up into 88 different zones that are named after the constellations that are in them. And this helps astronomers from around the world communicate which portion of the sky they are looking at to other scientists, because otherwise it would be very difficult to tell them where you are looking. The ancient constellations were named largely by the Greeks because the Greeks were the first people to develop telescopes and really start looking up at the stars and start thinking about what's happening outside of the Earth. And so because they were the first people to do that, they were the first people to name groups of stars. And so most of the names for stars we have come from the Greeks. So you may notice that they are named after, the constellations are named after heroes and villains and things that appear in ancient Greek stories. Scientists use a variety of different tools to look up at the stars and gather information about them. They use telescopes to collect light from stars, and this provides the images you may have often seen of stars and galaxies that exist distances from Earth. However, telescopes don't just collect visible light. They collect the entire spectrum of electromagnetic radiation or light. So that means that telescopes can actually give you more information about stars than just what they would look like to our eyes. Okay? For example, different ages of stars produce different wavelengths of electromagnetic radiation. So telescopes can collect that radiation and tell you the approximate age of a star. Scientists also use something called a spectroscope. A spectroscope is used to spread light out into its different wavelengths to be studied. Okay? This creates what is called a spectrum, hence the name spectroscope. Okay? It's going to spread that light out into a spectrum, and we can get lots of information from the spectrum of light that a star produces. We can tell what its temperature would be. We can tell its composition, so what elements is it made up of. We can tell how much energy the star has. Okay? Those are just a couple of things we can tell by looking at the spectrum of light produced by a star. Scientists also use light for other things. So aside from telling age and composition and energy and that kind of information, we can also use light to determine the brightness of a star. Apparent magnitude is a measure of how bright an object appears from Earth. Okay? So when we look up into the sky, we see stars and they appear different brightnesses to us here on Earth. There is a scale set up for magnitude, but it was set up by a person, a Greek, and he set it up by labeling all the brightest stars in the sky that he could see as having a brightness or a magnitude of 1, and then he went up from there. So as stars became less bright, he gave them higher numbers. Today, some of the bright objects in our skies have negative apparent magnitudes because they went back and assigned those magnitudes later on after this scale was already made. Okay, so here is an example of some different objects on this magnitude scale. Okay, so the sun is very bright in our sky, right? Because it's very close to us. So it has below a negative 25 brightness. Okay, Sirius, which you can see there on the bottom, close to 0, has a negative magnitude, whereas Vega is exactly at 0, okay? And then the faintest object that you are able to see with the naked eye, so without a telescope or anything like that, is just above a magnitude 5. So anything that is less bright than that in our sky, you wouldn't be able to see unless you had a telescope. Because some very bright objects are located far away from us and therefore don't appear very bright to us, because the farther light has to travel, the more of that light spreads out and the less bright things appear to us. So scientists wanted a way to indicate that an object was very bright even if it didn't appear bright from Earth. So they came up with a system called absolute magnitude, and you'll also hear this referred to as luminosity. Luminosity is the true brightness of an object. So instead of assigning this value based on how bright it looks from Earth, this is measured based on the star's temperature and the star's size. We also need to measure distance in space, but this becomes a little bit tricky. Okay? Because objects in space are very far apart from each other, using the common units like meters and kilometers and miles and things like that becomes cumbersome, because you're going to start measuring things in hundreds of thousands of millions of miles or kilometers, and that becomes difficult. So instead, we have 2 units that we use for outer space measurements. The first unit is called an astronomical unit, abbreviated as AU. 1 astronomical unit is equal to the average distance between the sun and the Earth, which is about 150 million kilometers. So you can see how measuring in kilometers would not work. Okay? This unit is used for measuring the distance between objects that are inside our solar system. It's convenient because it's easy to compare it to the distance between us and the sun and see, and it makes sense to our brains how far it is. But once we start to get outside of our solar system, objects get infinitely further far away from us, and so using astronomical units no longer works either, and this is the point at which we use light years. Light years are the distance that light travels in 1 year, and that is about 10 trillion kilometers. This is what we use to measure objects outside the solar system. This should be where your notes end, so then you can feel free to get started on your homework, which is the 12.1 check for understanding.